Hello everyone, this is Rikai Cui, and here I'm introducing a work on energy-based residual latent transport for unsupervised point cloud completion, which is a joint work with Shiqiu, Said Anwar, Jin Zhang, and Nick Burns. Unsupervised point cloud completion aims to infer the whole geometry of a partial object observation without requiring partial complete correspondence. Point cloud data, as a fundamental representation of 3D geometry, has numerous applications. Limited by viewing angle, occlusion, and acquisition resolution, real point clouds are generally sparse and incomplete. Therefore, completing partial scans is essential for a better understanding of 3D skins and beneficial for many downstream 3D computer vision tasks. To address this problem, previous work usually adopts a encoder-decoder architecture to train the model with large-scale datasets with both partial and corresponding ground truth complete shapes, where the latter is hard to collect. To tackle the difficulty in data collection, unsupervised point cloud completion has recently gained popularity due to its capability of utilizing both synthetic and real-world datasets. In the unsupervised setting, only unpaired samples from the partial observation domain and complete shape domain are provided, so we can use complete shapes collected from synthetic datasets like ShapeNet and utilize real-world scans. Existing methods leverage a one-to-one deterministic mapping to complete a partial shape. However, recovering missing geometry corresponds to a one-to-many stochastic mapping, since a single incomplete object observation can correspond to multiple valid completions. So we propose the first generative formulation of the problem. We assume that representations of a partial point cloud and its valid complete forms are close in the latent space. So we designed a latent space energy-based model in an encoder and decoder architecture, aiming to learn a probability distribution conditioned on the partial shape encoding. Furthermore, to train the latent code transport model and the encoder-decoder network jointly, we introduce a residual sampling strategy where the residuals captures the domain gap between partial and complete shape latent spaces. Next, I will detail our proposed method. I will first introduce the overview of our network. Then I will discuss the proposed latent transport. Our model consists of 4 main parts, namely an encoder for point cloud code extraction, a latent space energy-based model with energy function E theta to fill the code gap between the partial point cloud and its corresponding completion, a decoder for point cloud reconstruction, and a point domain discriminator to achieve adversarial training. Suppose Zx and Zy are latent representation of partial and complete shapes, respectively. We follow the conventional EBM formulation and define the conditional distribution of the complete shape latent code as equation 1, where E theta is the energy function parameterized by a deep neural network, mapping the code pair Zy and Zx to a scalar that measures their capability. To sample a data point from the EBM, we can use the gradient-based Markov chain Monte Carlo, for example, Lagrangian dynamics. This is summarized by equation 2, where we can iterate this equation to obtain a sample from the target distribution. In the unsupervised setting, we have no access to the paired partial complete point cloud samples. Therefore, we are incapable of directly modeling the capability of Zx and Zy through the energy function. Alternatively, we model the conditional distribution of the residual Rxy instead, representing the distribution gap between the latent space of the 2 domains. This is illustrated by equation 3. Different from the conventional conditional distribution of complete code in the supervised setting, The energy function here is designed to build the bridge between Zx and Zy, which we term latent code transport. The benefit of learning the residual instead of the complete code mainly lies in two aspects. Firstly, no paired partial complete point cloud data is needed for the residual-based EBM, leading to unsupervised point cloud completion. Particularly, we can define the initial state of Rxy as 0, representing no domain gap between partial complete point cloud codes. The model is trained to gradually refine Rxy. Secondly, it leads to joint training of the EBM and the encoder-decoder framework, which is significantly different from existing techniques, where the two models are trained separately. Given the EBM formulation, we can obtain a complete shapecode via equation 4. Here, we apply the stop gradient operation omega to avoid unfolding the Lagrangian dynamic iterations and involving the second-order gradient of Rxy in future gradient computation. We evaluate our method on ShapeNet datasets. Table 1 shows performance comparison on the dataset, where we adopt chamfer distance as the metric and compare with both unsupervised methods and supervised methods. This demonstrates that our method outperforms existing unsupervised methods with a large margin. This figure illustrates the qualitative result of our method compared with the competitive techniques. It can be clearly observed that our method can achieve better quality with more uniform point distribution and complete geometries. As the first generative unsupervised completion model, our framework can provide meaningful uncertainty maps that summarize the stochasticity of the inference process. Specifically, an uncertainty map is generated by performing multiple times of inference, and we define the variance of the multiple reconstructed complete point cloud as uncertainty. The general trend is as follows. Firstly, an area with low uncertainty indicates that this region or its symmetry correspondence has been observed in the partial shape, so that our model is confident with its prediction. And secondly, unobserved regions tend to have higher uncertainty, since there can be multiple variants to form a valid completion. For example, the plane vein is not observed in the partial shape, so our model assigns higher uncertainty score when approaching the end of the vein. Note that our model produces high uncertainty on outliers, such as the abnormal points in the table or chair sample. Thank you for watching. Please check out our paper for more details.